Perhaps that American politician was right. There are indeed things we know we don't know. For instance, cosmologically speaking, we know we don't know much, and certainly not nearly enough, about two of the enduring mysteries of the universe, dark matter and dark energy. It's little wonder that scientists are devoting so much grey matter and energy of their own to finding out as much as they can. Seen any big birds recently? IceCube has. If you think that's a cool name, you're right. IceCube is an observatory at the South Pole, and it saw a big bird back in December 2012.
IceCube is a neutrino telescope located at the South Pole, or to be more precise, under it. It consists of over 5,000 detectors that are spread out into a cube about a kilometer on each side. It's the world's biggest and its coolest telescope. IceCube has detected a handful of extremely energetic neutrinos. One of them, which is called Big Bird, has an energy of about 2 peta-electron volts. To give you an idea of how much energy that is, it is about 1 million times the energy of a dental X-ray.
Scientists have been using the names of critters from the popular TV series Sesame Street to designate major events that may help us better understand the particles that emanate from space. Particles like neutrinos.
So a neutrino is an incredibly small particle. It moves almost at the speed of light. It is nearly massless. It's incredibly plentiful, but it's very, very hard to detect because it will not interact with just about anything. If you could detect them though, because they have traveled through the universe essentially undeflected, they have information that you could not access in any other way.
The theory is that neutrinos are caused by violent events in space. In 2012, light from such an event began reaching Earth. This was a year-long outburst which happened 10 billion years ago in the unromantically named galaxy PKS B1424418.
What we have been able to establish for the first time is an individual blazar as a potential birthplace of an individual neutrino. The Fermi Gamma-ray Space Telescope has an instrument called the Large Area Telescope, which we use to monitor the gamma-ray sky, the highest energy electromagnetic band. And we just noticed that there was a tremendous increase in the amount of gamma-ray light coming from this one extragalactic blazar. A blazar is an extremely powerful, variable galaxy that is powered by a supermassive black hole. It went up not by a little bit, not by a few percent. It went up like 15 to 30 times its average flux. So we knew something was afoot. Later on, it turned out to be coincident both in time and in space with the neutrino that was detected by IceCube.
Working in conjunction with NASA's Fermi X-ray telescope, IceCube was able to link the cosmic neutrino it observed with that outburst from the gamma-ray blazar. The first time such a causal link between neutrinos and a single extragalactic object had been established.
The enormous increase in gamma-ray flux seen by LAT and radio flux by other Tanami telescopes let us finger the exact blazar which is responsible for Big Bird. This is the first time that we can point and say that blazar is where this neutrino came from.
Neutrinos and gamma rays are what Fermi is all about. It has already made some startling discoveries. One of its latest is finding the most distant and oldest blazars. Blazars are a type of galaxy whose intense gamma-ray emissions are powered by supersized black holes. These distant objects emitted their light when the universe was 1.4 billion years old, or just 10% of its present age. that they developed so early in cosmic history challenges current ideas of how supermassive black holes form and grow. Fermi has received an upgrade to improve its capabilities.
We see gamma rays, which are the highest energy form of light. And with each object that we see these gamma rays from, what we're doing is exploring some of the places in the universe with the most extreme environments.
The kinds of objects that we can study are pulsars and neutron stars, black holes, as well as dark matter.
So, to analyze these events, we have written a very long and complex program that basically uses all the information that was recorded by the instrument and figure out what is the direction of the gamma ray, its energy, and whether or not it's a real gamma ray and not a charged cosmic ray. So obviously software is really important for the LAT.
The software that we use to analyze the LAT data has gone through many revisions over the course of the mission, but PAS-8 is really the first revision of the software where we took into account all of the experience that we gained from operating the LAT in its orbital environment.
PAS-8 has made everything better, but one of the things that it's made better is that it's allowed us to open our gamma ray eyes to higher energies before, so that's a completely new view, and it's allowed us to open our gamma ray eyes at energies lower than before, so that's another completely new view, in addition to improving everything across the entire energy range.
The improvements that we've made to the software retroactively apply to all the data that we've collected. And so these improvements significantly enhance what we can do with the data that we already have, as well as the data that we'll collect.
Fermi's talents have also been concentrated on the search for dark matter, and in doing so it has observed unusual behavior in objects that remain unexplained. For instance, Fermi has discovered a gigantic structure in our galaxy, with what looks like bubbles extending above and below the galactic center. These are enormous gamma-ray emitting lobes. Each lobe is 25 light-years tall, and the entire structure may be only a few million years old. Within these clouds, extremely energetic electrons are interacting with low-energy light to produce gamma rays, but no one knows the source of these electrons. When studying these massive objects, scientists must look at the other end of the size spectrum for answers. Those at CERN in Switzerland are expecting great things from the Large Hadron Collider, after it too received an upgrade, an increase of power by 40%. In its new improved form, it is due to produce far more data than it previously did. The LHC has already revealed the Higgs boson particle. One of two types of fundamental particle, fermions or the other, in our standard model of the universe. What other secrets might it be about to unearth, as it were?
With an increased luminosity, we gain sensitivity at the highest energy. So suddenly, we will explore energies that hitherto were not really reachable. So if new physics is hidden there, this is the chance to see it. Some indications that created a lot of excitement with the theorists were seen with the experiment as there may be fluctuations, there may be real particles. As a physicist, of course, I hope that this is new physics already. But maybe that would be too simple.
The Higgs boson was the last puzzle piece in the standard model of fundamental particles and the forces which govern them throughout the universe.
What we really want is to understand the universe and why it looks and acts the way it does today. Our role as particle physicists are to figure out what the elementary particles are and how they fit together and interact, kind of like puzzle pieces, and the way the puzzle pieces fit together to give us a picture of the universe. Over the last 120 years or so, we've discovered all the individual puzzle pieces that build up to give us a theory called the standard model, which is kind of like the picture on the box. But we know that it's an incomplete theory. What we've essentially got is a small section of a puzzle picture that fits together very nicely and gives us all the particles that we see today, but we have no idea what the bigger picture is. The Higgs boson that we discovered in 2012 was the final piece in our standard model puzzle, and it was a fantastic discovery because it completed that small picture. And now what we can do is possibly use this Higgs boson to access the other parts of the puzzle. So our Higgs boson becomes like a Rosetta Stone to talk between the standard model particles and these new, what we call dark sector or hidden sector particles. So we're going to need to create many, many more Higgs bosons to be able to start seeing hints of this. And that's where the higher energy is useful. When we go to higher energy, it's almost as if we're getting a microscope to look on what we've discovered so far. It's possible that there are some very small differences in that Higgs boson, like the way that it decays, that we haven't noticed yet because we haven't had a strong enough microscope. But with a higher energy collider, with the LHC running at 13 TeV, maybe that is going to give us a strong enough microscope so we can see some small differences between our standard model theory and the Higgs boson that we have today. And maybe that'll give us some hint of some new physics that we can expect to come.
But it doesn't explain why nature prefers matter to antimatter, or what dark matter is. One theory that has been developed to answer these questions is what is called supersymmetry.
So one of the problems that supersymmetry could resolve is the mystery of dark matter. So this is something that astronomers and cosmologists tell us that there's an additional source of gravity in the universe which cannot be attributed to things we can see, stars, the nebulae and other things like that. And so at the moment this has the mysterious name dark matter. I think that's at least partly because we don't really know what it is. It's quite reasonable to think that it's a particle of a kind that we could potentially produce at the LHC, and supersymmetry, or at least some forms of supersymmetry, could explain that matter and predict its properties. So the main problem, if you ask most physicists, I think, that supersymmetry would explain is the mass of the Higgs boson. With the standard model as it stands, we cannot explain why the Higgs boson has the mass it has. It should be many times heavier than it actually is. So heavy that we would have no chance at all of seeing it in any foreseeable experiment. And this currently has no explanation. Supersymmetry would provide a very neat solution to that problem.
So, does dark matter? It certainly does. It makes up about a quarter of the universe. What is it? The short answer is, we don't know. The phrase was coined in the 1930s by Swiss scientist Fritz Zwicky. 4 decades later, Vera Rubin's studies of galaxy rotation confirmed his thinking. Galaxies have more mass than observable light would lead us to suspect. One suspect suggested by supersymmetry are the neutralinos, sometimes called WIMPs, or weakly interacting heavy particles. These particles act as their own antiparticle. They annihilate each other and release a flurry of secondary particles and medium energy gamma rays.
The LHC experiments are very capable to find dark matter. If, for example, supersymmetry is the symmetry which nature has realized, then I'm very confident that maybe even very quickly we can find, with the LHC experiments, supersymmetry. And that would be great. I mean, imagine we have taken roughly 40, 50 years in order to find and to really discover the standard model of particle physics. But that only explains 4 to 5% of the energy and matter density of the universe. I think LHC is the right machine to bring the first light, to shed the first light into the dark universe. There are more and more connections between space research and particle physics, but on the methodology, for example, and such things. But also on the science itself, there is a very strong connection, especially through dark matter. I mean, astronomers and astrophysicists will tell us in the next, I don't know, 10, 20 years with their new telescopes, they will tell us how dark matter, for example, has shaped the universe. And with the LHC, we will find what type of matter that really is.
These are some of the things we know that we don't know. But what if new physics tells us there are things we don't know that we don't know? The latest LHC data has turned up some interesting results.
In the data we took last year, we started to see a clustering of events, of diphoton events with 2 photons at a particular region of mass. The significance of that is not at this point very high. With more data, we don't know what's going to happen. There's a chance it could stay, but there's also a bigger chance that it will go away again. But which is going to happen, we don't know.
Physicists are keen to explore any glitch in the data.
The most exciting thing would be to find something that is completely outside the standard model. Even if it's just a hint that there is something more within our reach, just to give us an idea of where to look for new physics. There's got to be something out there. We know that our picture is incomplete, and we just have to find the right place to look for it.
For this year's running, we are running again at 13 TeV center of mass energy. But the big difference this year is we're going to run at a lot higher intensities, and we expect to get a much bigger data sample. So the experiment itself is ready and starting to take the data that's coming, and it really is shipshape waiting for the new data. At that point, of course, then we're looking in great detail and great depth at the data to try and understand what the physics is in the new data. And there's many different things we will be looking at with this new data sample. We will look again at the known processes of the standard model, which we've already seen at lower collision energies, and we started to understand and to measure with last year's data. But we'll also, of course, look hard at places where we might be able to see new physics starting to occur.
From the tiniest of subatomic particles to the immensity of galactic clusters, scientists and astronomers are looking into the past so as to see the future.
But when you think again about what we're exploring, when you think about the images that we're going to take, when you think about how far and away and how far back in time we're going to look, you can't help but feel like you're a part of something that's really important, that's helping us see not just about the past of the universe, but the past of us, where we've been and really where we're going to go.
If discovering the true nature of dark matter is successful, then we will have put together a picture of about 30% of the universe. There's still a lot more stuff missing, and it's called dark energy. Scientists have labeled dark energy one of the biggest mysteries in physics. Dark energy is the name attached to the force that appears to account for as much as 70% of the universe. Our fixation with dark energy dates from the late 20th century, when Hubble's brilliant revelation of supernovae showed us that the universe, approximately half its lifetime ago, was expanding more slowly than it is in our time. It started to speed up around 7.5 billion years ago. Why? Dark energy is the working name for the amorphous answer to that specific question. Is it a property of space itself? Does empty space contain its own energy? Does that energy increase as more space comes into existence? Dark energy has negative pressure. As dark matter is inimical to light, so dark energy repels gravity. At least that's how the theory goes. And to back it up, one major international effort is nearing the end of its scheduled working plan. Begun in 2013, the Dark Energy Survey, or DES, is an international project linking 400 scientists from 25 institutions in the United States, Australia, Brazil, Spain, the UK, Germany, and Switzerland. Its chief instrument is a 570 megapixel digital camera, DCAM, attached to the Blanco telescope at Cerro Tololo in Chile.
I'm a member of the Dark Energy Survey Collaboration, and I'm here on Cerro Tololo working to help commission the new dark energy camera that we've just installed on the Blanco telescope. The whole purpose of our project is to understand what is dark energy. Dark energy was discovered just less than 15 years ago, actually. In fact, using, in part, this very telescope. And it was discovered by its effect on the universe. So dark energy is our name, and it's just a name that we give to the phenomenon that's causing the universe's expansion to accelerate.
We're not trying to figure out if dark energy exists. We're not trying to find it. We know dark energy exists. We're trying to characterize it. We're trying to understand what it does to us, what it does to the universe, to its expansion rate, and to the gravitational attraction of things like galaxies. Over 5 years, the Dark Energy Survey will scan 5,000 square degrees of sky, far back in time and far away from us, in order to measure the distances of supernovae and the distributions of galaxies.
In some sense, the purpose of our experiment and what we'll learn by understanding more about what dark energy is to find out about the fate of the universe. What is going to happen into the future? Is the universe really going to keep expanding faster and faster and faster, or not?
Covering 5,000 square degrees of southern sky, the DES project is due to complete its search in 2018. Like the DES, some other exciting discoveries lie potentially just around the corner. While space-based telescopes continue their tireless scouring of the skies, their ground-based counterparts are poised on the brink of a dramatic new age. More than 3,000 meters above sea level, at Cerro Armazones near Paranal in Chile, ESO's ELT, that's Extremely Large Telescope to you and me, is nearing the start of its working life. With its stunning 5-mirror system, its diameter is an unprecedented 39 meters, making it the largest optical and near-infrared telescope in the world. Extremely large telescopes are currently one of the highest priority areas of development in ground-based astronomy. On ESO's ELT's job list will be the continuing search for exoplanets, examining the possibility, for example, of establishing contact with Proxima Centauri b, one of the likeliest candidates for Earth-like biological conditions. The ELT, attracting 15 times more light than the largest telescopes in operation today, will help detect water and organic molecules, a major step forward in our quest for extraterrestrial life, and make possible direct measurement of the speed of acceleration of our universe's expansion. Will it provide some of the answers we seek? Or will it show us collectively that we don't yet even know what we don't know? Is gravity an illusion? Do we need a new theory of gravity on a cosmic scale? As Einstein himself observed, the most beautiful thing we can experience is the mysterious.